This is the first video lecture about LR parsing. So I don't expect you to understand what LR means just yet. But in order to motivate why we're doing this, if you look at the algorithms, the algorithm that's implemented by Yak or Bison, underlying that implementation of the parser generator is the LR parsing algorithm. So it's a specific type of shift-reduce parsing algorithm, and we'll introduce you to these concepts. So that's the topic of this first video lecture, is to explain to you what LR parsing is and why do we need it. So if you look at the problem of parsing, parsing means you're given an input grammar and you're given an input string. And what you need to do is, if this input string is in fact recognized by this grammar, to provide the derivation or the parse tree for this input string. And for a compiler, you can see why this is useful. The input string would be a program. The grammar would be the grammar of a programming language. And the result would be a tree structure that we will use later on for code generation. So let's take this example here. We have a grammar, which is, you have a start symbol S, and it expands to two non-terminals, A and B. So there's only one rule here. And then there are two A rules. The A can expand to C, or it can expand to the empty string. So there are two rules with A on the left-hand side. And then there are two rules with B on the left-hand side. One generates two terminal symbols, C and B, followed by a non-terminal symbol, B. So you can see it's a recursive rule because B calls itself. So in fact here it's a write recursive rule. And that's the first option for expanding B. And the other option is two terminal symbols, C and A. There are two possible ways you can go about trying to show that this input string here, CCBCA, is in fact accepted by this grammar. The first is to go top down, starting from the start symbol S. And we say that, well, what can S expand to? It can be expanded by this rule, S goes to AB, and we get AB. We take this A and then use A goes to C to expand it to this C here. And then we take this B, use this rule, B goes to CBB. And so you can see that this rule over here is applied so that the non-terminal B from the previous step is expanded to the right-hand side of that rule. So CB and then non-terminal B again. And then the second time we choose to expand B, we're going to use B goes to CA. So you can see that the non-terminal B in the last step gets replaced with CA, and that's exactly the input string, right? So if you look at this input string here, it's exactly what is being derived. So we have shown that this grammar can generate this string, and in fact we've given a derivation for it. In this case, it's a top-down derivation. And if you look at the sequence of expansions of the non-terminal, we always expand the leftmost non-terminal. But as we saw in the previous lecture, there is the leftmost derivation where you expand the leftmost non-terminal. There's also an equivalent rightmost derivation where you always expand the rightmost non-terminal. So let's look at how that goes. So if you start from the start symbol, which is over here, we expand it using the only S rule there is. So there is really no choice there. So it gets expanded to AB using this rule. And now, if you look at the rightmost non-terminal, which is B here, we use this rule and expand it. So as you can see, I've taken that non-terminal B and replaced it with CBB. Since it's a recursive rule, the non-terminal B appears again after I use the rule. Now the rightmost non-terminal is this non-terminal B here, which I can expand using B goes to CA. And then the rightmost non-terminal is A, which I use this rule, and I replace it with a C. And you can see I get the same input string, except this time it was a rightmost derivation. In fact, when we're going bottom up, what we'll do is we'll start from the input string and work our way up until we can finally get the start symbol S. So we start from here and we try to end up over here. So that's a notion of going bottom up, from the input string up to the start symbol. Top down is the opposite. You start from the start symbol and you try to go step your way through the derivations to get to the input string. In bottom-up parsing, we're going to start from the string and work our way up to the start symbol to show that the input string is in fact recognized by the grammar. Shift-reduce parsing in particular, we're going to use this notion of reducing the string step by step into smaller strings so that eventually we get to the start symbol. So let's take an example. And there's a grammar that we're going to use in this example over here. And it's a fairly simple grammar. The only tricky part is this rule over here, which is taking an identifier, multiplying it with a term, the non-terminal t, right? So usually grammars are more general. This one only lets you multiply like an individual identifier rather than any expression. But this grammar is just for illustrative purposes. It's not something that we would use in our compiler directly. So let's take this input string, id times id plus id, and then try to work our way towards the start symbol. So the first step we'll do is replace this particular id by t. And the question is, so why did we skip over the first one and replace the second ID with t? And you can see the reason for that is I want to get to ID times t so that I can match this rule that I pointed out earlier, right? So this one, the t goes to ID times t. I need to match that right-hand side of that rule. And I can only do that if I replace the second ID with a t. So you can see that it's not always obvious which reduce action should happen first. It depends on the grammar and it depends on the sequence needed to get to the start symbol. Then I can replace that ID times t with a t, and I get t plus ID. And now I look for something to match in the right-hand side of the grammar and I don't find anything. So what I can do then is replace this ID with a t. I get t plus t. Again, there's nothing to match on the right hand side of any of the rules. So I can use the e goes to t rule and replace this t with an e. I get t plus e. And I can use this first rule over here and replace that with an e. And e here is the start symbol. So one of the things is by convention in a context-free grammar, the first rule by convention is assumed to be the rule for the start symbol. So in this case, we are assuming that E is the start symbol. And we've gotten to E, and so therefore this input string ID times ID plus ID is recognized by this grammar. The first E that we replaced was using the E goes to T plus E rule. That gave us the T plus E. Now the next application we did was e goes to t, then we took that t, replaced it with an id, then we took that one t and replaced it with id times t, and finally the last step to get to the input string is to replace that t with an id. So if you look at this sequence and you look at each of the non-terminals that was expanded, you can see that each of those non-terminals that are in the boxes there is the rightmost non-terminal in that line. We're always expanding the rightmost non-terminal. So this in fact is a rightmost derivation, except it's a rightmost derivation that's going from the input string, which is over here, step by step to the start state, the start symbol over here, which is the E. And so it is a rightmost derivation, but in reverse. If you keep track of each reduce action that the shift-reduce parser does, which as we saw is tracing a rightmost derivation in reverse, we can also draw out each reduce action in the form of a parse tree, or as we're building the parse tree essentially by keeping track of each of the reduce actions. So let's do the same input string with the same grammar and see how we can track the reduce actions to build a parse tree. I'm going to write the parse tree down over here, starting from the input string. And the first step was to reduce this ID to a T. So I could keep track of that action, the reduce action, and draw it as part of the tree over here. Now the next step is I'm going to take the first three symbols, ID times T, and replace it with a T, right? So I could say these three symbols got replaced with a T. And so if you look at these three symbols over here, is these three symbols, ID times T, and I can replace it with the T non-terminal. And now I have T plus ID. Notice I have T plus ID over here. The next step is to replace ID with a T, and then the next step is to replace T with an E, which I can show in the parse tree again in the same way. And then the last step is to take the T, the plus, and the E, and then use this rule to replace it with an E. So I get the start symbol E, and I can draw that in the parse tree in this way. So you can see how a shift-reduce parser can take each reduce action and then construct a parse tree out of it. So you can explicitly construct a parse tree, or implicitly you can see that there is a tree just by knowing what is the sequence of reduce actions and which rule was used for each reduce action. To test whether you understand all of this, I want you to write down the sequence of shift-reduce actions exactly the same way as we've done in this slide, and draw the parse tree for a different input, but using the same grammar. So let's introduce a bit of notation that will make it easier for us to talk about shift-reduce parsing. We're going to use this notation where there's alpha and then this separator, which is like a filled up circle or a bullet point marker. And so we'll just call it the separator for short. And this beta, so alpha and beta are strings, and the way that we define what alpha and beta are is we're going to use the regular expression language notation. So if you remember the definition of context-free grammars, so if I have s goes to 0, s1, and s goes to epsilon, then the non-terminals in this grammar, there's only one, which is s, and the terminal symbols are 0 and 1. And I'm not including the empty string here because that gets added in anyway. So the non-terminals here are just S, a capital S here, and the terminals are 0 and 1. So this N and T are defined for every context-free grammar. And so here this alpha is defined as the set N union with the set T 0 or more times. So we're taking this union of the non-terminals and the terminals and repeating it 0 or more times. So in English, instead of math notation, I guess you could say that you can have 0 or more terminals or non-terminals in any order. And that's what defines alpha. And beta can only come from the terminal symbols. So alpha includes non-terminals and beta only includes terminal symbols, and it can have any number of them, including 0. So both alpha and beta, if you look at this notation, either of them or both of them could be empty strings, right, because of the star. So the right substring is assumed to be this part of the input we haven't examined yet, and that's why it only has terminal symbols. And the left substring has both terminals and non-terminals. So you might have done some reduce action on the left substring alpha. The dividing point is marked by this separator over here, and it's not part of the string. Like, it's just a meta symbol that's used to keep track of where we are. Initially, all the input is unexamined, so we always start with the separator being on the extreme left. Beta, or the rest of the right hand side, is the input string. And so we're given a grammar, we're given this input string, and then we have this separator. We're going to keep moving it across the string until our goal is to have all of the input string scanned, and we have a start symbol at the end of this process, hopefully, if the input string is recognized by the grammar. So in shift-reduce parsing, we only have two kinds of actions. And we're going to define it using this separator notation that we just introduced. So the shift action moves the separator one place to the right. that means we shift the terminal to the left part, right? So if we have the separator here and we have a symbol right on the right of that separator, we're going to move it across and move X over to the left side. So that's called a shift, right? So we've seen this several times already, where we're shifting things onto the stack. And the reduce operation will apply a context-free rule to the string left of the separator. So if A goes to XY is a production, XY just to the left of the separator, then we can match this XY to the right-hand side of this rule in the context-free grammar and thereby replace the right-hand side with the left-hand side. So what I've done is done a reduce action. In this notation, the reduce action always happens right to the left of the separator. So if you look at this, it's the same example we worked out before, except using this separator notation. Every time there is a reduce action, it's taking whatever's immediately to the left of the separator, matching it to the right-hand side of some rule, and then we take the left-hand side of that rule, which in this case is a T, and replacing it there. So it's always going to be right next to this separator. So again, the same idea here is if I take this ID, match it to the right-hand side, replace it with the left-hand side, so I get a T over here, and so on. So the only difference between what we saw before and now is that before we only were looking at the reduce actions, and it wasn't really clear where in the string we were doing the reduce action. So we always said it's going to be the rightmost derivation, but if you're working from the string, it wasn't so clear what the first reduce, or in fact even subsequent reduces were, what part of the string should it target. So now we're making it explicit. It has to be exactly to the left of this separator, this marker. So what we can do now is, in addition to the reduce actions, we can show the shift actions, which is moving the separator until it's time to do the reduce actions. In this case, you're doing a shift of this symbol over here, so it ends up here, and then you move this over so that it ends up on the other side of the multiplication. And then you do a shift again, and at this point we are going to identify this part, match it to the right hand side, and do a reduce. Notice that I could have done a reduce over here, right? I had a choice between shift or a reduce with T goes to ID, but this one is something we chose not to do. Like we don't want to do this, because if we do that, we'll end up with T times ID plus ID, and there is no way that we can match this rule. This is the rule that we want for the multiplication, right? We need ID times T. If I end up with a T times ID, we are essentially stuck. We cannot get to the start symbol by doing that reduce action. So you have to be a little bit clever when we're doing these shift reduce actions, not to blindly do the shift or the reduce. You have to know kind of what you're doing, and knowing what you're doing is the basis of the LR parsing algorithm. So the LR parser is a way to decide at this point whether I should do a shift or a reduce. Whereas shift-reduce parsing essentially tells you, well, if you do a sequence of shifts and reduces, eventually you will get a parse, but it doesn't really tell you what the right order should be, right? So in this case, I know that the right order is to do a shift here, not a reduce. So the shift is correct, the reduce is wrong. Otherwise, I cannot get to the start symbol, which is what I want to do to show that this grammar can generate this string. That's essentially what we're going to study in the next this lecture and the next lecture as well, next few lectures actually, how we can decide when to do the shift and reduce so that if there is a path to the start symbol, that we will find it. In this case, if we do find that path, you can see that there is a sequence of deterministic steps I can take to get to the start symbol. And it's every time I just move this over until I get to the end of the string. At the end of the string, the separator's at the end of the string, and I get a start symbol, then I'm done. This notation is going to help us decide what is needed to be done in order to make shift-reduce parsing work as an algorithm. And just for completeness, let's take a look at how, when you're doing both shifts and reduces, how we're building the parse tree. It's fairly straightforward because we only build the tree on the reduce action. So we do a shift and then another shift and then a shift, and now we do our first reduce. As soon as we do that first reduce, we build that part, that subtree, which corresponds to that reduce action. And then we reduce id times t to a t, and then we move the separator over. So we shift, and now we reduce the id to a t, we reduce the t to an e, and then finally we reduce it to e, and now we're done. We have a completed parse tree, and we have a completed derivation that is built by shift and reduce actions. So the left part of the string, the alpha that was on the left of the separator, is implemented by using a stack, because as you can see, we're always pushing something on top of the stack. It's never modified except at the rightmost boundary of between the separator. So the top of the stack is the left of the separator, and then shift pushes a terminal onto the stack, and then reduce does two things. The first thing it does is it reduces using some rule. So it's always reduce using a specific rule. So this specific rule from this context-free grammar tells us, because each rule has a certain number of symbols on the right-hand side. So if I have a non-terminal, let's say A goes to W, I know that there is some sequence of terminals and non-terminals here, and it could be empty. So I can also have A goes to epsilon, right? So I can have any number of symbols, including 0 on the right-hand side of a context-free rule. And when I do a reduce, I take off from the stack the same number of symbols as the length of this right-hand side. So in this case, it would be 0. In this case, it would be the length of this string of terminals and non-terminals on the right-hand side of this A, and I pop them off the stack first. I remove them, and then I push a new symbol onto the stack, which is the left-hand side, or some symbol representing the left-hand side of the rule. So in this case, I would pop W off the stack, and then I would push A onto the stack, because that's the left-hand side of that rule. Possible in this shift-reduce sequence that you may end up in a state where more than one action is possible. And when you have more than one action, it may be invalid, like we saw before. I could do a reduce and it ends up being an invalid derivation because it doesn't accept the string, even though the grammar does accept the input string, right? It's just a bad shift-reduce sequence. But it's possible that there are two good shift-reduce sequences, because as we saw in the slide about ambiguity in context-free grammars, a grammar can be ambiguous if it has two leftmost derivations or two rightmost derivations. So in this case, if there are two possible rightmost derivations, then at some point you might have a choice between shift and reduce, or two reduces, and they're both valid. So if it's legal to either shift or reduce, it's called a shift-reduce conflict, and it usually can be fixed by using precedence and associativity. If it is legal to reduce by two different rules at the same instant, so there's two sort of parts to the left of the separator on top of the stack, those are equivalent. So if I have two choices between two different rules, that's called a reduce-reduce conflict. In this case, there is a genuine ambiguity in the grammar. And it's possible that if there is no ambiguity in the grammar, but there is a reduce-reduce conflict, that it can be fixed using additional look-ahead. So there's two possibilities. So there's either there is ambiguity, or it's not ambiguous, but you still have a reduce-reduce conflict, in which case you might want to look ahead in the input to make a decision as to which one is the right one. So when to shift or reduce? So let's look at this same example and consider this step. We know that it's legal to shift at this point because we'll end up with a situation where you match this right-hand side. Because I do ID times ID, I would reduce that ID to T. I get this right-hand side. However, at this point, when I'm when I have this separator right before the ID, I could reduce instead of doing a shift. And when I do that, I end up with the T times ID. It causes a fatal error because there's no way to reduce to the start symbol E. We saw this earlier as well. So this just to emphasize that a reduce is possible, but it's not a valid action. So we need to only do valid reduces when we are constructing this derivation or building the parse tree. Another question to see whether you're understanding. So for the same input, try to find a different shift-reduce choice in the derivation. So I showed you this example on this slide, but if you go back to the slide where we go through the entire derivation, look for another shift-reduce choice somewhere in the derivation where a shift over the reduce leads to this state over here, which, as we can see, cannot be reduced any further because E would be right before the separator, and you couldn't reduce E any further because the only place that E occurs on the right hand side is over here, right, with the parentheses. So this ends up being the derivation in which there is another shift reduce choice, and a shift is the correct decision, and the reduce is not a valid action. Just to give us some additional notation to talk about this will be useful when we cover the algorithm for LR parsing, and it generally helps us be more formal and precise about what's going on in the parsing algorithm. So I want to define these two notions, a viable prefix and a handle. The intuition is that we want to reduce only if we can eventually reach the start symbol. So as we saw, there are cases where there's a shift reduce choice, but only one of them is actually a valid action. So let's assume a rightmost derivation. So in this case, S in 0 or more steps can get to alpha x beta. In this case, alpha and beta are strings of symbols. So whenever we use Greek symbols, they stand for some mixture of terminals and non-terminals, or just terminals. It depends on the definition. So in this case, I have alpha here, which is any sequence of terminals and non-terminals. Beta, we can assume is just terminal symbols, a string of them. And I have a rule in my grammar which is x goes to w. Then I can replace the x with the w in a rightmost derivation. When I'm doing the reduce action, as we saw, we're going backwards, right? We're taking the w, which is the right hand side, and replacing it with the left hand side, which is the x. So I'm taking this part of the derivation string and replacing it with this non-terminal. And as we go further and further back, we end up with the start symbol. So this rightmost derivation notation is useful because this alpha w, which is over here, we call that a viable prefix. Essentially, we keep shifting, we do some reduces, and then we keep shifting again. At some point, we'll end up with alpha w. And alpha w is a valid prefix because w here can be replaced with an x. And this is true if there is a rule x goes to w. So in the context-free grammar, we have a rule x goes to w. We can recognize when to do a reduce. So this is a valid reduce action. And the w itself, this part over here, is called a handle. And a handle just means that's the right-hand side of some rule where we want to replace it with the left-hand side. So notice that crucially, a viable prefix is not every possible place you could do a reduce. It's a valid place where you can do a reduce. And we'll see how we can determine the valid from the invalid when we look at the parsing algorithm. But before we can look at the algorithm in detail, we need to first be familiar with this notation and how we talk about these derivations in a formal sense or mathematical sense so that we can reason about the algorithms. The handle always appears on top of the stack, right? It's never the case that we are reducing anything other than the symbols that appear on top of the stack. So that's an important constraint. So if you look at the bottom-up shift-reduce parsing algorithms, we are going to be studying a few of these. So they are all called LR, and the L stands for the fact that we are scanning the input from left to right. So we're always kind of going from the start of the program towards the end of the program. That makes sense. Sort of as humans, we are familiar with reading. We always read kind of left to right in most languages. I guess there are some languages where you read right to left. But there's always an ordering, right? So in the conventional ordering for English is left to right. So that's what we're going to be using in the algorithm. So we're scanning the tokens from left to right, and we're always producing a rightmost derivation. We always want to make sure that we're creating a rightmost derivation so that we know when it's truly ambiguous. So if there's two possible rightmost derivations, we know that the grammar is ambiguous. And the K is the number of tokens of look ahead. So typically, if we do have look ahead, K equals 1 is usually sufficient, especially when we're doing shift-reduce parsing. The first special case we're going to consider is LR0, where we have 0 tokens of look ahead. That means that I'm going to make, when I shift, of course, I'm shifting 1 token at a time. What the 0 refers to is how much context you need to look at in order to decide when to do a reduce. Right? When have you found a viable prefix to do a reduce action? LR0 says I need 0 tokens of look ahead. And we'll see that algorithm first because it's the simplest to understand. And then we'll see its limitations. And then we'll see that we can extend it a little bit by looking at one symbol of look ahead. And that's called simple LR. It's simple because it turns out that there are more complicated LR algorithms. So we'll look at some of these. The algorithm that's used in Yak and Bison is LALRK. So it'll take us a little bit of time to work our way towards that algorithm. So we need to go through a few steps first. And once you understand the more basic algorithms, then it'll be a lot easier to understand the specific algorithm used in Yak or Bison. One nice advantage of shift-reduce parsing is that the parsing algorithms work with left recursive grammars or right recursive grammars. As we'll see later in top-down parsing, it's a bit harder to work with left recursive grammars. We'll see that in more detail later on. All of these algorithms are based on the main problem, which is recognizing a viable prefix. So once we know how to recognize a viable prefix, we know when to shift, we know exactly when to reduce. And so all of the LR parsing algorithms are based on recognizing viable prefixes. Unfortunately, we can only identify viable prefixes for a subset of context-free grammars. Not every context-free grammar can be parsed in this sort of deterministic shift-reduce manner. Adding look ahead helps. So adding 0, going from 0 symbols of look ahead to 1 or to K symbols of look ahead can help you decide what is a correct viable prefix at every point in the parse, but not always. Like it doesn't help with every possible context-free grammar. So if you only focus on this subset of context-free grammars, and we're making the assumption that this subset is expressive enough for all of the grammars we would write for programming languages. So programming languages, as we know, are designed, and they're designed to be unambiguous. So the subset of context-free grammars that can be used for shift-reduce parsing should include all of the programming languages that exist and even people might come up with in the future. And that, at least that's a claim. So of course you can come up with something explicitly that would make it difficult to parse, but that's kind of self-defeating because you're creating a programming language that would be deliberately hard to parse, which kind of doesn't make sense. So for these subset of context-free grammars, LR parsing is a deterministic and a linear time parsing algorithm. So it's deterministic, so there's no ambiguity for these context-free grammars, and it's fast. It's linear time. So as soon as it sees every token of the input, it's done creating the parse tree or the derivation for that input. So what do these subsets of context-free grammars look like? So here's a sort of graphical view or a Venn diagram of this. So if I have the space of all context-free grammars, so this is any context-free grammar that you can write, and every context-free grammar in this set has an equivalent context-free language, right? So these are all the possible context-free grammars. If you take a subset of those, is the subset of unambiguous context-free grammars. So these are grammars for which every input only gets one parse tree. But that set is still too big to recognize all viable prefixes. So there is a set of LRK context-free grammars. So LR, remember, means left to right, rightmost derivation, with K symbols of look ahead. So it's some constant K. That's now a subset of the unambiguous context-free grammars. You can subset that further to get the grammars that are used by Yak and Bison, called LALR. And they are small, sort of almost the same as LRK. They're just more efficient in terms of time and memory usage. And if you subset that even more, so a further subset of those LALRK context-free grammars are the simple LRK context-free grammars. So they still have look ahead, but it's a simpler algorithm. It's easier to understand. And then finally, we have the LR0 context-free grammars, where it's still left to right, it's still constructing a rightmost derivation, it's finding the viable prefixes, but it's doing so with 0 symbols of look ahead. And it's the simplest of all of these parsing algorithms to understand, so that's the one that we'll be doing first.